Hello, welcome to week 7 of computational quantum chemistry. So this week we are going to discuss about potential energy surfaces. As we know, the potential energy surfaces is central to chemistry and chemical reactions, and potential energy surface is obtained when it's basically when the nucleus moves in a potential created by the electron that we have already discussed. Now before going into the potential energy surface, I want to show you something curious, and that is leopard in IIT Bombay. So, IIT leopard spotting is quite common in IIT Bombay campus, and I am a professor, associate professor in the IIT Bombay. So, we often have this news that leopard has entered the campus, and this is one of the news I pulled up from 2022. Now, you may be curious that why I am showing leopard when I am discussing computational quantum chemistry. Well, they can give us insight. Now, question is that how leopard enters into IIT Bombay campus. So, IIT Bombay campus is just bordering. Here is the IIT Bombay campus. It's nestled between two lakes. This is Vihar and this is Powai. Sorry, the name is not visible here. And this is bordering basically the green part is Sanjay Gandhi National Park. So, this is from here actually the leopards enter the campus. Now, question is that how does leopard enters into the campus? So, let me ask you the reverse question, how can you go to Sanjay Gandhi National Park from IIT Bombay? Well, I can take a cab, and if you go by Google map, it shows 46 minutes if you take a cab. Walk will take 4 hours, if you take a public transport it will take around 1 hour some minutes. So, this is how you will go, you will come out of it, take a road and then you will go. But what this one does? Of course, it does not have any access to Ola or Uber, so it cannot go by a cab. So, the way it enters the campus, if you go back to the map, so this is Sanjay Gandhi National Park and these are the two hills. If you are aware of contour plots, this actually shows that this is at elevation. And you see there is a gap between these two hills, and if you go to a satellite map and zoom it in, you will see something like this. There is a faint hint of a path which goes through these two hills, and that is what this leopard do. So, nature always follow minimum energy path. So, it goes from one place to the other place by following a path which actually have lowest energy. And this brings us to the definition of potential energy surface. So, a potential energy surface is actually looks like like a geographical feature where you have valleys, where you have mountains, you have passes. So, the point 1 which is marked is both 1 here is actually a minimum energy place, which is the ground state, which is like a valley. And what is the ground state in terms of energy? So, if you are in the ground state and from the ground state if you go in any of the direction, your energy will only go up. And this the point 2 is what is a transition state. So, transition state basically connects to valleys. It is like a saddle point, and transition state specially is a saddle point of order 1. And in the case of its a transition state, what will happen is that energy will be minimum, energy will go up in every direction only except 1. So, if I think of this point, the energy will go up if I go this way. So, only one direction, if I go from this way, the energy will come down. So, in the case of transition state, energy goes up except one direction. Now, why one direction energy gives up? Because these are like the paths through which you can go from one valley to the other, and that is what you are looking at the potential energy. Now, question is that if you give more energy, will it be cause the reaction help faster, because reaction is nothing but it crosses from one valley, from the reactant valley to the product valley. And this goes through this transition state or the minimum energy pathway. Now, question is that if I give a higher amount of energy, will it cross the path more quickly? Well, if you give it a higher energy, you may also jump to the higher order settle point where you are in the top of the mountain. And if you are on the top of the mountain, when you come down, you can come down in multiple ways. So, you can go to the multiple valleys. So, there are many ways down, but which one lead to the desired product is not very clear. So, the main assumption in this case is that the most probable path connecting the reactant and product has the lowest possible energy, but one need to cross a certain amount of barrier to get there. Now, how do I get the minimum energy path? How do I get first the minima, the ground state? So, I get the minima by finding the point where my derivative of the energy with respect to the coordinate is 0 for every value of r. Question is that how do I found that point? I have to use some optimization algorithm like steepest descent, conjugate gradient. Optimization is basically a mathematical technique. We will not go into the details of the mathematics of it because we are just going to use it, and these optimizers are generally available in form of standard software packages. So, we are just going to get it. Now, how do I get to the point at d by dr is equal to 0? So, first of all, the first thing I have to do to get it 0 or not, first I have to calculate this one. And how I can calculate? I will use the fourth postulate. So, if I have an well behaved wave function, and I will just replace this Hamiltonian by the derivative Hamiltonian, and that will give me the corresponding property. That is what the fourth postulate tells, that if I have a well behaved wave function, I can just replace the Hamiltonian by a derivative Hamiltonian, and the corresponding expectation value will give the corresponding property. So, this is where I am going to calculate the gradient. The question is that how can I say it is a real minima? So, the gradient only tells that it is a sum of a saddle point. It can either be a maxima or a minima. So, I can say it is a real minima by checking it that the second derivative is positive or not. So, second derivative in this case will be related to the Hessian matrix, and that will be related to your IR frequency. We will come into more discussion about the IR frequencies, but the trick is to check that if the point is a real minima, then in that point the second derivative, the Hessian, in this case IR frequencies will be positive. All of the IR frequencies will be positive, and that is the check to say that it is a real minima. If one of them is negative, then that is a transition state. If more than one is negative, then it is a higher order saddle point. Now, question is that is it a global minima? It can be, it may not be, because I am only, when I am doing this optimization, I am only sampling a part of the potential energy surface. So, maybe I have reached the one minima, but that minima may not be the global minima, may be there is some other value available which actually has more lower energy. So, to find out global minima, you need specialized algorithms. Orca has one of them, what is called a GOAT algorithm, and we will see how this algorithm work in one of the examples. So, in the case of general optimization, if my energy goes up in all direction and my all frequencies are positive, the only thing I can say that it is probably a minima. It is a global minima or not, that is very difficult to predict, and actually it is almost impossible to guarantee that there is a global minima. Now, question is that when I do this optimization, which coordinate I should do the optimization? The most easiest is to Cartesian coordinate. The molecule is described in terms of XYZ coordinate of each atom in the 3D space. Advantage is that it is very simple. It gives a direct representation of the atomic position, making it straightforward to define the geometry of the molecule. Secondly, it is universal, it is applicable to all molecular geometries regardless of symmetry or connectivity. Disadvantage is that for a system of n atoms, only 3n minus 6 is independent. So, the extra degrees of freedom must be handled very carefully. And second problem is that adjustment to the coordinate, one coordinate will often lead to the large changes in geometry, and that makes the optimization very slow. So, that is very generally very inefficient to optimize in terms of Cartesian coordinates. So, generally optimization in any quantum chemistry software is never performed in terms of Cartesian coordinate. So, what you do is that you switch it to what is called an internal coordinate. So, internal coordinate, the molecule is described in terms of bond length, bond angles and dihedral angle, which are the intrinsic to the molecular structure. Advantage is that optimization converges faster because internal coordinates align closely with the chemical relevant changes in the geometry. I only need to optimize only relevant 3n minus 6 coordinate, there is no redundancy, and if I want to put better control, like if I want to change only one of the bond, or I want to scan the potential energy surface along one bond, this approach is generally, internal coordinates are generally much more helpful. And when we will do potential energy surface, most of the time we will use internal coordinate. Now, what is the disadvantage? To transform between Cartesian and internal coordinates are computationally very expensive and not always straightforward to larger complex molecules. Second thing is that for non-bonded systems, the interactions or the interaction between very flexible molecules, the internal coordinate can be very difficult to define and less reliable. And for some of the molecules, if you try to define the Z matrix, you will often see, if you try to do it by hand, you will see it's quite problematic. And it can have particularly problematic when the angle approaches 0 or 180 degree. For that, it will lead to numerical instabilities. What is a redundant internal coordinate? In the redundant internal coordinate, it includes not only the standard set of internal coordinates, but also additional redundant geometric parameter to fully describe these molecular geometries. Now, for a water molecule, there in the internal coordinate, there is a 3 coordinate, 2 OH-OH bonds and the H-OH bond angle. Now, the 2 OH-OH bond, because water molecule has a particular symmetry, you may consider them to be identical before doing the optimization, and you can do it without putting the constraint also. If you optimize it properly, the both bonds will anyway come same. Now, in the redundant internal coordinate, you also have these 3 coordinates, these 2 OH-OH bond and H-OH bond angle, and you also have an additional fictitious bond between H1 and H2. So, you will get total 4 coordinate, and this makes the optimization more easier. But remember, in the redundant internal coordinate also, you need a part of it is defined in terms of internal coordinate. Now, you see, in most of the cases we give our geometry in XYZ or Cartesian coordinates. So, what happens is that the program automatically converts it from Cartesian coordinate to internal coordinate, and also it puts the redundant coordinates. Now, this conversion actually requires taking inverse of a large matrix. So, sometimes taking this inverse become very complicated if your molecules are very large, and so even doing the calculating the wave function or the gradient, your conversion from Cartesian to internal coordinate becomes more costly. So, for that you have special kind of optimization algorithm, we will discuss into that. Now, we have learned a little bit of theory, now try to do some practical. So, let us optimize formaldehyde. Formaldehyde is a common molecule. So, where the CO bond is, these are experimental parameters, CO bond is 1.205 angstrom, the CH bonds is 1.111 angstrom, and this bond angle, the OCH bond angle is 121.9. So, let us see if I optimize it using different methods, how the performance is available. And we are going to optimize using Hartree-Fock. 2 DFT functions, one is a GGA, that is PBE, one hybrid B3LYP, MP2, and of course, one of the double hybrid, and we are going to use Def2QZPP basis set for our calculation. So, let us try one by one. So, I made an Excel sheet already. And this Excel sheet, I have already done some CCSD T augmented C 5 zeta calculation. This result I have taken from the literature. I have not done the calculation myself, to be really honest. And you can see that if you do to CCSD parenthesis T and use a large basis set, this is how the results you get. So, these are very good agreement with the experimental value. Now, let us of course, CCSD parenthesis T calculation can be possible with ORCA, but the way we installed the ORCA, we have not installed the AutoCI module. So, with the present version it is not possible, but if you are interested to do CCSD T parenthesis T calculation, you can install the AutoCI module yourself and do the calculation, but you can take this value as it is also. So, let us start the calculation. So, the first thing we will do is to open Avogadro and make the geometry. So, I need a carbon, I can remove one of the hydrogen, I can replace the other hydrogen by an oxygen, bond order is double, adjust the hydrogen, and then I can do a quick optimization to make it a CO. So, now what we will do is that we will put and we will make the our input file. So, in place of single point energy I will write geometry optimization, and using def2 qzvp, and we are going to use Rij cos x. Make the input file name as h2co hf.inp. So, my input file is generated. So, I open it here in terminal. It shows some error. Let us see what is the error. There is a spelling mistake. In place of cos x, I have written cos x first and then s later. Okay, we can correct it. I can maybe prepare the PB input file. So, here it will be PB and this will be only Ri. So, now all my calculations are done. Let me start with the simplest of the one which we did first is the H2CO HF. So, now if I open the output file, you will see that what it does is that it first writes the value in terms of redundant internal coordinate. So, here there are 3 bonds. So, 2 HC bonds and 1 OC bonds, and then there are 3 angles, and additionally it puts a constraint on the dihedral. So, here if you see how what was the initial value is 1.088, 1.255 and 1.085. Sorry, I told 1.088, it is 1.0855. And if I go back to my slide, this is how the actual values looks like. So, of course, the initial optimization we did with molecular mechanics is actually not very good enough. So, we need to do proper optimization. And so, it start the geometry optimization cycle, it will take the Cartesian coordinate, convert it into internal coordinate, actually redundant internal coordinate, and then do the Hartree-Fock calculation. And after the single point energy calculation is done, it does the gradient calculation by doing what is called a CPSCF, and then after the gradient calculation is done, it checks the value of the gradient and take the geometry optimization relaxation step, and there are criteria on the RMS gradient, maximum gradient, as well as the step size what we have taken, and the optimization has not converged, more geometry cycles are needed. So, it goes to a next cycle with the new geometry, and this is how the optimization goes on. And after certain number of cycles, all these 4 parameters comes down below certain threshold, and once it happens, it's all the parameters are converged. You will see that this word hooray, the optimization has converged. So, it means now the optimization has converged and the final values are one 1.0923, 1.1765 and 116.05. So, this is how it will look like when I will, and the optimization actually happen after 7 steps. So, when the optimization is completed, it actually again do the single point energy calculation, and then actually it finds out what is the possible values. Now, if I want to see this one visually, what I can do is I can open the output file using ChemCraft. So, you can also optimize the animation, and it shows how very slowly it changes. So, one of the major changes happen from the first step to the second step. If I do that, is a changing of the bond. So, my initial bond lengths were much larger and then it gets shortened due to the optimization. So, if you want to see what was my initial bond length, is 1.2521, and after optimization it has become 1.176. So, there is a considerable shrinkage. So, you can also plot the energy versus the step number, and if you see the energy in the first step, let me try to show it again if it is not clear. So, I will go to optimization, I will go to tools, and I go to trajectory analysis tool, show property versus step n, and then you can actually plot any of this, but I will just plot the energy just to show you. So, this is how the first step, there is a huge decrease in the energy, then it almost remains flat, and then the convergence actually happens. And you can actually see different parameters here. So, this bond length, or if you want to see the angle, you can see the angle also. So, this is how you can do. So, now let us plot it one by one, so that I can get idea about how the numbers actually looks like. So this is my, no, I should see from here. So this is my CH bond length. This is my CO bond length. And this is my angle. So if you see in terms of from experiment, all the parameters, the two bond lengths and bond angles actually, and one bond angle show considerable deviation, and couple cluster was giving much more accurate numbers, almost close to experiment, whereas Hartree-Fock is not giving so much accurate. So the electron correlation shows actually has an important effect. Now check the DFT numbers. Let us first see the PBE. I can directly open the output file. And I go towards the end. Optimization is successful. So these are the final values. .2075. And the angle is 115.87. So if you compare with respect to the Hartree-Fock, the PV values are actually pretty good, and the angle may be slightly problematic still, but in terms of the other things, the values are actually pretty good. Now one interesting thing to notice here is that this is a TEF to QZVP value. What happens if I go to triple zeta? So one of the easy way to do that, to check it, is to run a calculation with the triple zeta basis set, because we want to see how much is the basis set effect. So I will run it. TZVP, I will save it as and I want to do this calculation quick. So what I will do here is that I can always restart my calculation from already optimized geometry. The way I will do it is that after the calculation there will be an H2CO pb.xyz file has generated, which contains the optimized geometry. I can go and show it to you. So this is the final optimized geometry is given here. So instead of starting the optimization from the starting coordinate, I can start my optimization from my already optimized geometry. So I can instead of using XYZ, I can use the XYZ file option, and I read it from H2COPB.xyz. So what you will do, it will start from already optimized geometry, and hopefully the optimization will be much more quicker. So I go H2CO PBE TZPB.INP. H2CO, PBE, TZV, P to out. And by the time I think we can open the B3 it is pretty quick. So, the convergence only happen at 4 cycles. So, I get the triple zeta result. And you can see that the triple zeta and quadruple zeta results are not very different. And that is the case we have discussed in the case of DFT. The basis set convergence is actually much faster than the wave function based method. So, triple zeta results are generally good enough in most of the cases. Again, it is a very common practice to optimize the geometry in a much lower level of method than what you are doing the single point calculation. So, it is okay to optimize the method using a smaller basis set and maybe a cheaper method and do the single point calculation on that optimized geometry on a much higher level method using larger basis set, and the small errors which happens due to the wrong geometry generally gets cancelled out between the two structures. So, it is a very common practice to have that. Now, let us check the B3 lip. So, in the case of B3 lip, you can see that the bond lengths are almost of similar quality as well as the angle, but it's not may not be the always been the case. The angle may be slightly better than the PB, but the difference are actually very minimal. It will be interesting to see the amplitude thing. So, although in the case of MP2 the angles may not the bond length may not be super much improved. In the case of angle, actually there is some improvement. Now, question is that how much is the MP2 result deteriorate when you go to triple zeta basis set? We can also check that one. although the MP2 calculation can take some time. So let us go H2CO. Let me save as H2CO. MP2 .inp, and this I should read the MP2 geometry. It's RI MP2. I have to give a F2 TZVP/C. I have to give an auxiliary basis. H2CO MP2 TZ. There is an error. Okay, we can check what is the error. It's written def 3, it has to be written def 2. Okay, we can check what is the error. We have not written how to treat the exchange. Fair enough. So I have to write Rij cos x. So by the time this job runs, we can see the B2PLIP output file. So in the case of B2PLIP, the values are quite good as an MP2 can get. Maybe slightly better than the MP2 in few of the cases, like here this is slightly better. Now the question is that is MP2 better than the DFT functions? That's actually a very debatable topic, and first of all you need a large basis set. def to QZVP is at least what you will need to do and reliable MP2 level calculation. Okay, and the MP2 job is still running, and now it's done. One can see that the changes are slightly larger in the case of MP2 from going to triple zeta to quadruple zeta than what you have seen in the case of the DFT functionals like PBE. Although this gives you a good result in many of the cases, but it's not true that MP2 is actually a very good approximation to get geometries, maybe for very well behaved closed shell molecules, but if your system has a little bit of multi-reference character or they are open shell, they can give you a lot of problems if you optimize the geometry with MP2. And next we are going to see an example when we will see a problematic case how the MP2 performs for geometry optimization.